Welcome to Chef Dean Academy, and today we'll be explaining one of the very important topic in structural analysis, which is the wind load analysis, and we'll be using BS 6399 Part 2 as our reference code. According to the code, you can actually analyze wind load using two methods. We have the standard method and we also have the directional method. So that standard method make use of simplified procedure, and it allows for manual calculation, in which the results you obtain from this standard method are actually conservative compared to the second method, which is the directional method, which make use of complex procedures. So before you can actually use directional method, you need some computational analysis, but the advantage is it gives a more accurate result. So if this is your first time coming to this channel, please kindly subscribe to this channel, or if you have been coming and you've not been subscribing, please kindly subscribe so that whenever I upload a new video on structural analysis or structural design or building construction or civil engineering topics, you will actually be notified. So to start with, wind load is one of the dominant environmental load that can actually be acted on a structure. So the question now is, how does wind affect our structure? There are three types of force in which wind can actually impose on structures. The first one is the uplift load. So wind tends to push or pull the roof of a building upward by either when the wind is flowing under the roof. When wind flows under the roof, it tends to push the roof upward, and when wind flows over a roof, it tends to pull it upward, as you can see with this directional arrow. Then the second type of force in which wind subjects our building to is the shear load. This one is actually found in due to the internal pressure exerted by wind on the building. So this actually causes cracking of walls, and this might make the buildings to tilt. Then the last type of force in which wind exerts on our building is the lateral load. So we can actually see this include pushing and pulling of walls, and this might actually cause the structure or building to slide off the foundation or overturn. So in the next, continuing with this video, I'll be explaining the step-by-step procedures that you need to follow in order to analyze wind load. The first step is you need to obtain your design parameters. Design parameters include the location of your building, the altitude of site. This is taken from this is obtained by taking the mean sea level as your reference point, then the closest distance to sea, the closest distance of your structure to the sea, then the overall length of the structure, then the center of frames. The center of frames come into play when you are dealing with frame structures or portal frames or industrial buildings. Then finally you have the height of the building. So these are the basic parameters that you need to analyze wind load. So is to classify your building. So building can be classified according to clause 2.2.3.2 of BS 6399, and the building is classified into three parts. You have the part 1 classification. The part 1 classification is when the height of your building is actually less than the length of the building or the width of the building. So that type of building is a part 1 building. Then you have the part 2 building. Part 2 building is when the height of your building is less than the length of the building, as you can see, but is greater than twice the width of the building. Then the last part is the multiple part. This one is when the building is actually greater than twice the width of the building. The essence of classifying your building is actually to obtain the reference height. From the diagram here is indicated by HR in the code. So this reference height is equivalent to the effective building height. So you need your effective building height, which is the HE, in order to analyze your wind load. Once you've able to classify your building, the next step now is to obtain your basic wind speed, which is the VB. So basic wind speed is actually obtained from meteorological data of the location in which your building is sited, and these include the hourly basic wind speed of the location. So once you obtain the basic wind speed, then you can now obtain the site wind speed by reducing your basic wind speed or factoring it with factors such as the site altitude, the directional factor, the seasonal factor, and the probability factor. The seasonal factor is used to adjust the basic wind speed, as I said earlier. So it's given by this formula 1 plus 0.001 delta S. So delta S is the site altitude, which is equivalent to the altitude of the site from this the site altitude of site, which is the second design parameters. So the altitude of site is actually what you need in order to calculate your site altitude. Then the second one is the directional factor. The directional factor actually depends on the orientation of your building, and you can actually obtain this from table 3 of BS 6399 part 2. And whenever the orientation of your building is unknown, just like in most cases, in some cases, you can take your directional factor to be 1. And the next factor is the seasonal factor, which is SS. It depends on the building exposure to wind, how your building is being exposed to effect of wind. So when we have a permanent exposure to wind over a continuous period of time for like 6 months, then you can take your SS to be 1 also. Then the last one is the probability factor. So for design in which the adjustment for risk is made through partial factors, like when you are designing your structure in such a way that you give some allowance for your load, like you are applying partial factor of safety, then in such case you can actually use your probability factor. You can take your probability factor as 1. So once you obtain your site wind speed, so once you obtain all these data, you can now calculate your site wind speed based on clause 2.2.2 by using this formula here. So the next step after you've obtained your site wind speed is now to obtain the effective wind speed. So the effective wind speed is a factor of the site wind speed and this factor that we call SB. So SB is the terrain and building factor. So you can actually obtain that from table 4. So I've actually indicate table 4 in this presentation. So to obtain your SB, you first need to get your effective height. The effective height, we've actually obtained it from our building classification. Then once you know your effective height, the next thing now is to determine the closest distance to C of your structure. How close is your structure what is the closest distance of your structure to the sea? Once you also know that from the design parameter, Then the next thing now is to now determine if your structure is located in country or if it is located in town. According to BS 6399, a structure is located in town if the structure is located in build-up areas not less than 1 kilometer upwind of site, with an average level of rooftop of at least 5 meters above the ground level, in which your location of the building is either town or country. So if it is in town, that means the building is located in build-up areas in which we have buildings that the top of their roof from the ground level is actually above 5 meters. So when your building satisfy this, that means it is located in site. But if it does not satisfy this, that means it is located in country. So you can now decide if you are going to use this part of the table or you are going to use this part of the table. So then once you know your location of your structure, then you know the effective height, then you know the closest distance to the sea, you can actually obtain your SB. So once you obtain the SB, then you can calculate the effective wind speed based on plus 2.2.3.1 of the code. After obtaining your effective wind speed, the next thing that you now need to obtain is the net surface pressure. The net surface pressure is actually the algebraic sum of the external surface pressure and the internal surface pressure. So the external surface pressure is given by this formula, which is QS CPE QS is the dynamic pressure, which is calculated as 0.613 VE square. We knew VE before. VE is the effective wind speed. So that's how to obtain your dynamic pressure. So once you obtain your dynamic pressure, the next thing that you now need to obtain is your external pressure coefficient, your internal pressure coefficient, and you also need to obtain your size effect factors. So the next slides will be giving us insight on how to obtain these 3 or 4 parameters. To obtain the external pressure coefficient, the external pressure coefficient actually depends on the orientation and the type of building that you are dealing with. This is actually given in clause 2.4 to clause 2.5 of the code. If you check through the code, you see various type of building and the corresponding external pressure coefficient. So in this tutorial, I just try to give us examples on 2 type of structures that you actually use that are actually common in order to determine their external pressure coefficient. So the first thing that you need to do in any type of structures that you are dealing with, the first thing is you need to first of all classify your building. So for any table, there are a lot of tables in this clause, in clause 2.4 and clause 2.5. So in any table that you want to use, you actually have a key to data. So this figure is used to classify your building. So it's actually to divide your building into zones. So as you can see, when your D is greater than your B, the B is the cross wind width of your frame or of your surface. For example, let me show us a typical example. Let's say so looking at this building here, you can see when wind is blowing at the 0 direction, you will be taking this side of the building as your D, as your crosswind breadth. Then when wind is blowing at the 90-degree direction, you will be taking this side of your building as your crosswind breath. I don't know if you understand. So once you've able to determine your D, so you can see from this table, before you can actually calculate your external pressure coefficient, you first of all need to determine your D over H. So D is the crosswind breath width of the structure. The capital D is the overall width of your structure, while the small b is the crosswind breadth of your structure. So when your D is greater than your B, that means you'll be dividing your structure into 3 zones. But when your D is less than your B or equals to B, you'll be dividing your structure into 2 zones. So once you know this, then you can actually come to this table and obtain your external pressure coefficient based on the zones. Then this one also give us another example of external pressure coefficient for a dual pitch roof. You also have external pressure coefficient for mono pitch roof. So this one is general when you are dealing with portal frames. And what you just need is you need to calculate your pitch angle. So as you can see from this symbol, pitch angle is actually indicated here. Then once you get your pitch angle and you classify your building into zones, so from the zones, then you can actually obtain your external pressure coefficient. Then once you obtain your external pressure coefficient, then you can now move on to the internal pressure coefficient. The internal pressure coefficient is given in the code based, like the internal pressure coefficient is actually divided into 2. You can have for enclosed building and you can have for building with dominant openings. As you can see, table 16 give internal pressure coefficient for enclosed building. So you need to know if your structure is an enclosed building or if your structure is a dominant opening building. So a dominant opening building is defined as one in which the area of the building is equals to or greater than twice the sum of the opening in other faces, which contributes to the porosity of the internal volume containing the opening. I don't know if you understand that grammar, but you can actually check through the code to obtain your internal pressure coefficient. But generally, most of the structures that we deal with, such as residential buildings, industrial warehouse, they are mostly enclosed buildings. So for enclosed building, you either use 0.2 as your internal pressure coefficient or you use minus 0.3 as your internal pressure coefficient. So then for dominant buildings, when you are dealing with dominant buildings, what you just have to do is you need to find the ratio of your opening to the sum of the remaining openings and distributed porosity. Then it's just a factor of the external pressure coefficient. So once you're done with obtaining the internal and the external pressure coefficient, you can now determine the last parameter in that equation, which is the size effect factor. The size effect factor is actually divided into 2. You need to calculate size effect factor for the external part of the building and also the size effect factor for the internal part of the building. So for the external part, you first of all need to calculate the diagonal dimension. So the diagonal dimension is actually given in table 5, in figure 5, depending on the type of structure that you are dealing with. So this one is for portal frames. So this one are for this one is when you want to determine your load on individual faces of the building. And this one is when you want to determine your load, when you want to use a combined load on the and when you want to combine the faces of your load. Then once you get your dimensional factor, the diagonal dimension, then you can now obtain your side factor from figure 4. So what you just need before you can obtain your side factor, you first of all need to obtain the effective height of the building. Then you also determine if your building is located in country or it is located in town. So once you determine that, then you can now read, let's say the effective height of your building is from 15 meters to 20 meters. So that means your building is located in countries. That means you can now use this part of the table to determine the your size factor. So let's say our building is effective height is 15 to 20 and the closest distance to C is greater than 100. So that means we'll be using B on this graph. So what you just have to do is, after you've calculated your dimensional dimension, then you just trace up and get your size factor, which is on the y-axis of this graph. So this one is for the external pressure. Then for the internal pressure, is actually divided into enclosed building and dominant opening buildings. So you can use this formula for enclosed building. If your building is an enclosed one, you just have 10 times the cube root of the internal volume of room. Then if you are dealing with dominant opening buildings, you use this formula. So once you get your diagonal dimension using this formula, then you can actually use this table, this graph also, to obtain your size effect factor. So once you're done with the calculation, then you can now come back to this formula and get your external pressure coefficient and also the internal pressure coefficient. So once you get that, then you can now find the net surface pressure on your building, and this is actually the wind load on your structures. So thanks for listening. Make sure you subscribe to this channel, and if you have any question regarding this tutorial, kindly comment below. See you next time.